Thank you, Henry. I am Davide Portinari, a PhD student in the Projects and Calculations Office. And today, along with Julien, I am presenting you this seminar on neutron detectors and data acquisition, for which we also have to thank for their help Paolo Mutti and Bruno Gerard, the ILL instrumentation experts. So I will be giving a bit of context following what Julien explained about helium-3 proportional counters, and I will be talking about how we can retrieve energy and timing information about those events. And then we will follow up the data acquisition following these detectors, analyzing the analog and the digital chain and trying to make some comparisons with them. Then in the second part of the seminar, I will present some other neutron detectors, scintillators in particular, and to see how the digital chain can be exploited to analyze the pulse shape coming from the scintillators, and also to see how scintillators are a crucial part of the experimental setup that makes up for neutron imaging devices. So here is what Julien has already explained us. When a neutron essentially reacts with a proportional counter, we have the production of tritium and a proton particle that will leave a trace of charged particles that get accelerated inside of the chamber and get finally collected to the anode of the chamber, and they will cause a current to flow into the circuit. So what we can detect from the electronics devices is a very small and short signal that will be in the order of magnitude of the millivolts. And what we are really interested in, as is already been said, is the integral of this signal, because it is there that we have our proportionality with the charge that was deposited inside of the proportional counter, and ultimately the proportionality to the energy of the particle. So the way we perform this is by putting a preamplifier as close as possible to the detector so that we can ramp up this millivolt signal to something that is hundreds of millivolts. And we can at the same time integrate these signals so that we have something that is finally proportional to the energy of the particle. What follows after the preamplifier is essentially a split, because what we want to do is, yes, record the output energy of the particle, but we also want to detect the time of arrival of the particle, because as we know, with these neutron detectors, we are not able to straight away retrieve the energy of the particle, but we have to employ some time of flight or similar spectroscopy methods in order to retrieve our energy histogram in terms of arrival particles. So the way we perform this is either by following an analog approach or a digital approach, as we will see. In the analog chain, we can repeat, we are saying that we have a arrival signal at the detector that gets pre-amplified following a charge-sensitive preamplifier that will leave us with a signal that is proportional, yes, to the charge deposited in the detector, but it will also have a very, very long decay time that might be a problem in terms of dead time and in terms of counting rate that we can achieve, as Julien has explained as well. So what we put straight away after the preamplifier in the analog chain is a shaping amplifier. The shaping amplifier will keep the proportionality between the peak amplitude and the energy of the incoming particle, but it will give us with leave us with a much shorter signal that we can exploit much faster, and that won't paralyze the detector for as long as it would if we left it at the preamplifier stand. As we said, in parallel, what we are doing is we are processing the timing information of the particle, and this fast amplifier will leave us with a signal that is much shorter and will not have any proportionality with respect to the energy of the particle, because on this line, what we want to do is just retrieve a timestamp to associate with the particle in order to perform time spectroscopy with it. So the way we go about finding this time step is deriving this fast amplifier output and go look for the zero crossing of the derived signal with respect to the baseline, because the delay that comes from this zero crossing is not dependent on the type of pulse or on the amplitude of the particle, and so it is essential to guarantee the time resolution of this time measurement. So if we have a broader look at the analog chain now, we can repeat that we have here the fast line and the energy line. Into the fast line, we will have what is called the discriminator. A discriminator is something that will impose a threshold on our signal so that we can flag the arrival of an event over all the open window of our detection. But what we will do is not to impose a threshold directly on the input signal, but rather on the timing filter that derives the signal coming from the input. Because if we were to impose a threshold directly onto the input signal, then we might give rise to some bad triggers or even to some missed pulses. So once the timing filter is triggered and we have flagged the arrival of an event, the logic unit will go on about pairing this information with what is being processed on the energy output. And that is essentially an analog to digital conversion of the peak that we get from the shaping amplifier, because as we said plenty of times, it is proportional to the energy. What happens is in the digital chain, on the other hand, is an analog to digital conversion that happens much, much earlier in the processing chain. It will happen, in fact, straight away out of the output of the detector, and this signal will be fast analog to digital converted straight away into a sample stream that will be a very, very thin discretization of the analog signal into all these sample points that make up for the same shape, of course. But the problem with this is that we will have a very, very big bandwidth, a very, very big stream of data that will come continuously from the detector. And in order not to let it overflow our memory buffer, we need something that will get this amount of data down to something from gigabytes to something like kilobytes or megabytes. So it is the user itself that will provide some feedback into the digital pulse processing by manually and by programming this field programmable gate array with a tailored approach that is related to the science that it needs to perform with this analog signal. In particular, of course, he will be interested in time and energy information, but what he might be interested in is also, for example, the pulse shape of this analog signal, as we will see later on. So if we have a look at what these kind of algorithms that are set by the user look like, we would find something that is very similar to what the analog chain was doing. So we will have a split after the sampling happens in the decimator to the timing information, where we will be again deriving, finding a zero crossing, and finally providing a timestamp to our event builder. While on the energy side, we will have some energy filter that is called a trapezoidal filter that performs very much a similar role to what we saw with the shaping amplifier. What we can see is that in the energy part of the algorithm, it is very important to have a baseline subtractor, because if we take a look at, for example, at this input, we have what would look like two overlapping pulses, and they both have the same apparent amplitude. But we can see how the first one has a much bigger amplitude with respect to the relative amplitude of the second. So by subtracting the actual baseline of these two pulses, we are able to retrieve the real energy related to both of the particles, and then we can perform that kind of discrimination that Julian was talking about and say, maybe this is a gamma ray, it is below the threshold, we will reject it, it won't add up into the event builder, while maybe this one, yes, it is a neutron, then it will very rightfully go on and follow the data acquisition path. So this is pretty much how the digital chain works, and we have to keep in mind that it is very important that once we do this decimation point where we are sampling the points from our input, we are basically completely detaching what is the acquisition chain with respect to the processing chain, meaning that once we get the data from the input, we are not paralyzing the input while we are processing all this information, meaning that we can multi-process many events, store them in a memory buffer, and the acquisition chain is not affected. We can go on and virtually have a a detector with no dead time at all that can endure a much higher counting rate with respect to what is able to do an analog chain data acquisition. So this is one of the main advantages of the digital chain, this multiprocessing, but it also has the undeniable advantage of multi-parametric capabilities, allowing so to replace these all multiple analog components following back to back into the chain with only a single digitizer. And it also has the potential, as we said, to preserve the pulse information, because for some detectors, it is important to have information on the pulse, as we will see. And last but not least, the digital chain has the big advantage to perform a coincidence analysis without having to manually and physically, let's say, construct and manufacture cumbersome matrices of coincidence units. So it is not only very handy for the scientist in terms of tailoring the type of science and the type of processing that he needs from his data, but it is also very much cost effective as the improvements come along. So what I want to talk about now is I would like to kind of shift our attention for a moment from proportional counters that are essentially what mostly drives the science at the ILL, and have a look at scintillator detectors as the ones we have, for example, on FIPS or low and grand, but as the ones that also make up for the imaging detectors experimental setup. So while in a proportional counter, the driver of the signal is the ionization of the filling chamber in order to have these electrons amplified and then collected at the anode, what drives the signal in a scintillator detector is the scintillation principle. So how does scintillation work? Essentially, we have a scintillator molecule that will have an interaction with the energetic particle we're interested in, and this interaction will lead the molecule to go into some kind of excited state. And then it is the de-excitation from this excited state back to the ground state with the emission of a photon that is the process of scintillation itself. So it is with these photons that we will be able to drive on the signal and follow up the data acquisition. So when this de-excitation happens from a singlet state, we would call it fluorescence, while when this happens from a triplet quantum state, the de-excitation is called phosphorescence. And in order to have some more information on these scintillators, we can say that they are mainly grouped in terms of organic, inorganic, and liquid scintillators. And some of the most important features, kind of similarly to what was laid out for proportional counters, would be the efficiency of the detector in interacting with the particles we are interested in, the linearity of the light output that it is able to give with respect to the incoming energy of the particle. The transparency of the scintillator is very important, and scintillator, we would call it transparent if it is virtually able to emit photons without reabsorbing them, because if we had the emission of photons that would then cause the absorbance again from the same molecule, then we would be, of course, affecting the linearity of the energy deposition itself, and this would be very much detrimental, of course. Then some other features comprise, of course, the manufacturing. The easier it is, the best the scintillator will perform, and a fast decay time. It is, of course, always very very good for any detector. So even though the most ILL scintillator detectors are used for gamma rays, we can just as easily use these scintillators for neutrons. And in particular, if helium and boron were the most used elements for detection in proportional counters, we have lithium that plays a role in scintillators. We will see that it has a slightly smaller cross-section, but a higher Q value. But most importantly, it is very chemically similar to sodium. So sodium iodide is comprised as the best inorganic scintillator, a kind of benchmark to which we refer all of the scintillators. And so we can build just as similarly a lithium iodide scintillator that will have a proportional performance. So if we are to look finally at a design of one of these scintillators, we would see that we have the scintillator part that is here on the left, while this big box on the right is the photomultiplier tube. And we will talk about it in a moment. So we have the thermal neutron that is interacting with the scintillator. It is causing the nuclear reaction with, for example, lithium, as we said, with the emission of an alpha particle and a tritium particle. And these ones will start to excite the scintillator molecules that will start emitting low energy photons kind of everywhere. So the purpose of the photomultiplier tube is now to collect these low energy photons and to convert them into primary electrons by the use of a photocathode. The photocathode is a multi-alkali compound that with a certain quantum efficiency will be able to make this conversion for the photomultiplier tube. Then in the second part of the photomultiplier tube, we will have an increasing energy field where these primary electrons will start to bounce off dynode after dynode, and this acceleration and this multiplication of electrons will bring us with an output of a very high voltage signal, meaning that in this case, for scintillator detectors, we don't need another preamplifier after the photomultiplier tube. The photomultiplier tube is the preamplifier itself. What I want to ask myself now is essentially, what if I have now a gamma ray interacting with my scintillator? Because as we said before, for proportional counters, this is not much of a problem because we are dealing with a gas. And so the interaction of gammas is pretty much less important than the interaction of more charged particles with higher energy deposition. But if we are dealing with the scintillators, as I said, it is virtually a solid material or a liquid material. So gammas will have a much more important energy deposition in there. And we cannot use this method to discriminate gammas against neutrons. So what we do is we analyze the pulse shape, because there is a very important feature of these scintillator materials in providing us with a different pulse shape with respect to the particle that is interacting. And in particular, gammas will have a chunk of the signal that will be very small for higher timescales in the pulse shape, while this will be the opposite for heavier particles such as alpha or tritium. And this is a very specific feature that comes from the nature of fluorescence and phosphorescence. So gamma rays will be more likely to cause fluorescence because of their lower energy deposition, while alpha particle and tritium particle, because of the nature of scintillation itself and the higher energy deposition, will be more likely to populate these triplet quantum states that have a much bigger time scale and the kind of delayed scintillation phenomenon that will cause the pulse shape to be more shifted to the higher time scales. So how do we exploit this in order to be able to discriminate between neutrons and gamma? Well, if we remember what we were saying for the digital chain data acquisition, it will only be enough to open 2 gates instead of 1 gate for the integration of our signal. We will have one of them that integrates the whole signal, while we will have another one that will integrate only the first part of it. So once we make the ratio between the energy deposited, or at least the pulse that makes up in the tail of the pulse shape with respect to the total pulse that comes from the integration of the total window, then we will have something that must remain constant depending on the particle that is hitting the detector. And as we can see from this graph in the bottom right, we can see that regardless of the amplitude of the originating particle, we will have this very linear performance of the pulse shape discrimination algorithm. So this is a very powerful tool that comes from the tailored digital pulse processing that a user and a scientist can obtain from pulse shape discrimination. Last of all, as I said, I wanted to give a mention to neutron imaging. That is a non-destructive technique that allows us to investigate the structure of any target object in a very similar way to what is done with X-rays radiographies, essentially, but with the very, very important asset of being more sensitive to low Z elements, so heavy, lighter nucleus, such as hydrogen or boron or any scattering or capturing lighter element, because it means that in principle, we are able to investigate the dynamics of liquids and lighter elements inside of metal casings that, in the case of X-ray radiography, would be shielding all of essentially the imaging that we are able to get from this coffee machine. So this is a very, very interesting industrial application that gets some attention in the internal combustion engine industry, and at the ILL, it has led to the development of some fuel cell tomographies in order to try and investigate the recombination of hydrogen and oxygen inside of these very cutting-edge energy devices. So how does this neutron imaging work in terms of experimental setup? We will have the neutron beam colliding with our target object and leaving essentially behind him a neutron footprint on the scintillator material. The scintillator that is used in some of these cases is a zinc sulfide activated with silver and enriched, of course, in lithium in order to obtain the neutron detection. But the problem of this quite efficient scintillating powder is that it is not transparent to its own light. So what we have to do is we have to build a quite thin scintillator in order for the photons not to be reabsorbed by the scintillator and to maintain intact our neutron footprint. And then these photons will have to reach in some way what is a very standard CMOS camera that is operating in integration mode, meaning that the photons that we are emitting from the scintillator can just as easily be detected by the pixels of the camera, and opening the standard acquisition window of the camera, then frame by frame, we will be able to reproduce such a nice image as this one. What is the problem with this, though, is that both gammas and neutrons don't really go well with these CMOS cameras. So what we will have to do is to put in place some very heavy external gamma shielding in order to prevent the surrounding radiation to spoil our nice images. And then what we will have to do is also put in place some kind of mirroring system that is very simplified in this picture, but it is very important not to have any neutrons going to vitiate the performance of this CMOS camera. So this is everything I wanted to talk about. So I thank you very much for your attention, and I thank once again our experts for their help, Paolo Mutti and Bruno Gerard.